Kriging with external drift. Introduction and grid creation.
This is the fourth Geostatistics course about Kriging and Cokriging interpolation and mapping. As a part of this fourth Geostatistics course, you have already available the following lessons: Ordinary Kriging, Universal Kriging, and Regression Kriging. Actually, we are working on the Kriging with external drift. In this lesson, you will learn how to create a full grid using only QGIS. We will also discuss the unique characteristics of creating a grid for Kriging with external drift. To access the premium courses, go to the Geo RGB community website at geoscourse.online. Choose the course you are interested in and enroll. Once you have registered, you will have access to all the content and can begin learning. Here, as you can see, we have already loaded the introduction for the fourth Geostatistics course. The first lesson that is about Ordinary Kriging, 2 hours 30 minutes of content. The second lesson that is about Universal Kriging, 4 hours 30 minutes of content. The third lesson that is about Regression Kriging. Here we have several parts, and in total it's 9 hours 30 minutes of content. And now we are working on the fourth lesson that is about Regression Kriging. And now you have already loaded the first part, that is an introduction and also how you can create a grid for performing Kriging with external drift. Remember that at the website you can download all the scripts that we are using during the lesson. Universal Kriging, Kriging with external drift, and Regression Kriging. Geostatistical techniques often use multiple terms for similar methods, causing confusion to users. However, Universal Kriging, Kriging with external drift, and Regression Kriging are essentially the same technique. Many authors use the term Universal Kriging specifically when only the coordinates are used as a predictors to define the trend surface. Here we have an example of the Universal Kriging where we fit the first order trend surface on the dataset. In this case is the Wolkamp aquifer. This example comes from the second lesson of the fourth Geostatistics course about Universal Kriging. I recommend to watch that video tutorial. What we have here is two different views from the same model. Here we have the X and Y coordinates, and for the zeta axis what we have is the groundwater elevation. Then here we have two different types of values. One associated with the trend surface, that is the deterministic model, and the other value is associated with the residuals. The residuals is the difference between the observed values, that is the dots, less the deterministic model, is the values on the plane. And the important thing in this case is that this trend surface fitted between the data was created using the X and Y coordinates. And that's what defines Universal Kriging. The term Kriging with external drift is preferred when the drift or deterministic part of the variation, also known as a trend surface, is defined externally as a linear function of certain explanatory variable rather than the coordinates. Then when we are using Universal Kriging, we are using the X and Y coordinates to define the trend surface. But when we are using Kriging with external drift, we are going to use another variable that is not the X and Y coordinates. It's a different variable, and that's the main difference between Universal Kriging and Kriging with external drift. In both Universal Kriging and Kriging with external drift, predictions are made using the same principles as Kriging, but with the inclusion of auxiliary predictors in the model, either coordinates in Universal Kriging or an external explanatory variable in Kriging with external drift. The trend and the residuals are modeled together, but the trend must be linear in both cases. It means that when we are using Universal Kriging or for kriging with external drift, the trend surface is going to be created with a model that is a linear one. We cannot use other type of models, has to be a linear one. And that's one of the limitations of using this kind of kriging techniques. The advantage is that we can model the trend surface and the residuals together. But the limitation is that we can use only linear models in order to define our trend surface. Regression kriging is a method that estimates the trend and the residuals separately and then sums them. In this method, any type of model can be used for the trend part, not just a linear model. And that's a big advantage compared with the other two techniques. In this case, we can use any type of model. Then it makes the model more flexible, that can be adapted better to our data set. However, in this case, the disadvantage is that the process is going to be more complex, because in one hand we have to deal with the trend surface, and the other hand we have to deal with the residuals. And when we are using universal kriging and kriging with external drift, we are doing all the process in just one step. And that's the main difference between the universal kriging and kriging with external drift with the regression kriging. The model that we use to define the trend surface and how many steps we have to do in order to complete the Kriging interpolation. Here we have an example based also in the World-Camp Aquifer dataset where we was using a generalized additive model to define the trend surface. And this example comes from the third lesson of the fourth Geostatistics course about regression kriging. I also recommend to watch this video tutorial. Let's talk a little bit more about kriging with external drift. In kriging with external drift, an additional variable known as an external drift is included in the interpolation process. The external drift can be any variable that is thought to have an influence on the variable being interpolated. For example, imagine you are trying to predict the temperature at various locations in a city. You have collected temperature measurements at several locations in the city, and you also have data of the altitude in each location. You may choose to use the altitude as external drift in your kriging model, as it is likely that the temperature will vary with the altitude due to the impact of the temperature on the air density. By including the altitude data in the Kriging model, you can improve the accuracy of your temperature predictions by better capturing the spatial patterns in the data. In this example, the altitude is the covariate, and this variable has to be recorded in both at the sampling locations and at the prediction locations. From this information, we can extract two very important things. The first one is that the variable of interest, the variable that is going to be interpolated, has to be spatially correlated with the variable that we are going to use as external drift. Okay? In this case, the variable of interest is the temperature, and the variable that we are going to use as external drift is going to be the altitude. And as we can see, the temperature is depending on the altitude, and that's the correlation between these two variables. And another very important thing is that the external drift variable has to be recorded in both at the sampling location and also at the predicted locations. The predicted locations is that locations where we don't have any sample, is the unsampled locations, and is the locations that are going to be defined at the grid interpolation. Then at the grid interpolation, each pixel needs to have the external drift variable. In this lesson, we will use QGIS to create a grid for our prediction locations, including the external drift, the covariate. We previously learned how to create a grid with R, but we will focus on using QGIS in this lesson because it is more intuitive and will help us better understand the concepts. Using QGIS will also make it easier for us to complete the process. To create a proper grid for Kriging with external drift, it's not something easy. There are a lot of things involved. For example, the shape of the grid, the dimensions of the pixel, the variables that we want to add for each of these pixels. And we can do this process with QGIS, and we are going to visualize everything, right? Because when we are working with R, sometimes just writing the coding, it is not easy to understand what we are doing, right? But when we are using QGIS, you can visualize everything, and that helps a lot to understand what we are doing, right? And in this case, for Kriging with external drift, the grid is quite complex, and with QGIS, you're going to understand very well all the concepts. For this exercise, we are going to use the Meuse River dataset, a very interesting dataset related to contaminated soils that is pretty common to use for examples of geostatistical studies. We are going to use R in order to download the Meuse River dataset. This dataset is located at the package SP, that is for spatial data. And inside this package, we can find three different files: the Meuse grid, and the Meuse River. Then let's go to load the library. Now let's go to load the dataset, that is the Meuse. For us, this one is going to be the important one because it's where is located all the data, right? The Meuse grid is going to be interesting for us in order to know what is going to be our goal with QGIS, because what we want at the end is to replicate the results that we have here in this package associated with the grid, okay? Then now we can check the data frame if we click here at the data panel. And as you can see in this data frame, what we have is the X and Y coordinates. They are in UTM. We have 4 different heavy metals, that is cadmium, copper, lead, and zinc. We have also the elevation of the terrain, the standardized distance to the river, from the sampling location to the river. Also, we have the organic materia, we have the float frequency, the type of soil, and other different parameters. But for us, the interesting one is going to be the distance to the river. We are going to calculate that one with QGIS, and we are going to add that information to the grid that we are going to create. Then the next step is to create a backup. I like always to create a backup of the data set, okay? And I'm going to call this one as a Meuse B, but it is the same, okay? Now the next step is to export this data set in this format, CSV, in order to open this data set on QGIS. Then we have to indicate where we are going to save this file, okay? Then I created a folder, is this folder, and I want the file, the data set inside this folder. Then I copy the link, and I paste from here to here. And also I have to change the direction of the dash bars, because in other way it's not going to work. And also I want to save the spreadsheet with this name, okay? You can add whatever you want. I added this name, Meuse data, okay? And also I added this information over here in order to have a proper spreadsheet. Then we can run all these lines. I'm using this script to export the data frame to the spreadsheet. Then now if we go to the folder, now we have here the data set, and we can open this data set with the Open Office. And as you are going to see, we have the same data as I show you at the data frame. X and Y, the heavy metals, the elevation, the distance to the river, and the other parameters. Then we can close this one. Now we are going to add a spatial structure to the Muse River data set. Then we are going to say that the X and Y, they are coordinates, and as they are coordinates, they have a spatial location. Then we can run this line. And now we can plot with the next script. We are adding here the data frame. Then we can plot. And now here we have a map with the sample location. The next thing is to load the next file that is going to be the Muse River. Then we can run this line. We load the data. We can see the class of this file. As you can see, this one is a matrix. And now we can plot the river on this map with the next script. And here we have the map. Then this one is the samples. And what we want to do in our grid is create a grid where we have from each sample location the distance to the river. Later we are going to see that one more clear, okay? At the moment, let's go to carry on. And now let's go to load the data associated with the grid. Is the next script. We can see the structure. And as you can see, the structure also is a data frame. Then as this one is a data frame, we can see the parameters that we have in this data frame. As you can see, we have the X and Y coordinate. We have the parameter part A, the parameter part B, the distance to the river, the type of soil, and the float frequency. And in total, as you can see over here, we have 3,103 observations, okay? That's the total number of points that we have inside that grid with the information, with this information that we have at the data frame. One very important thing that we have to understand is that the grid is just a data frame. As you can see, okay, the class is a data frame. And that's very important because if we understand that the grid is a data frame, we can add any parameter to this data frame and then make this data frame as a grid, right? And that's very important. Then let's go to move on. The next one is to see the class, but we know already it is a data frame. And now we are going to add a spatial structure to this data frame in order to see the spatial location, right, of this grid. Now we can plot the grid, and as I said before, we have this grid that has in total 3,000, let me show you here, 3,103 observations. That's the number of pixels that we have here. It is not yet a pixels, but you have to imagine that each square of these ones is going to become a pixel later, okay, with the different transformations that we are going to do with the grid. And that is what we are going to do now with the next script. We are going to provide to this grid topology, right? Then with the next line, we gridded the Muse grid, and now we can plot with the SP plot to see the graphs. And now you can see that we have the different parameters that I showed you before at the grid, right? In this grid, we have the part A, part B, distance, type of soil, flow frequency, and that's all this information that we can see over here in these maps. And the goal for today is create this grid using just QGIS. You are going to learn how to create this shape, how to add the dimension of the pixels, how to add inside this grid the external drift, the variable associated with the external drift, and also you are going to learn how to add any type of variable inside this grid. As we are going to discuss later, you are going to see that the distance to the river is the external drift in this case, and this parameter is spatially correlated with the zinc concentration, because the river is the mechanism of transporting the contaminated sediments that are rich in zinc. When we are working with the package SP, we have already the Muse grid created. We don't have to do anything. We have to load the file and it is created. But the point is how we can create this type of grids for any other project, right? And that's very important. And it is so hard to find information about how to create this type of grid. And here, with the lesson for today, you are going to learn it. Let's go to start with QGIS.
If this tutorial is helpful to you and contributed to your professional development, we kindly ask that you consider supporting the Geo RGB community. Your support is greatly appreciated. There are various ways in which you may choose to support the community. 1. Show your support by leaving a like on the Geo RGB community's YouTube videos and turn on notifications to stay informed of new uploads. Additionally, leaving a comment in the comment section can greatly aid in sharing the content. 2. Consider becoming a premium member on the Geo RGB community website, geoscourse.online. The cost is very reasonable, and not only will you be supporting the community, but you'll also gain access to all the premium content. 3. Creating free content is time-consuming and requires a significant effort. If you find the material valuable and would like to support the creators, you may also consider making a donation. 4. Another simple and effective way to support our community is by following me on LinkedIn. This way you can stay informed of my new monthly content, and by liking and commenting on my posts you will be helping the community. Your comments in LinkedIn is highly valued and really makes a difference. Thank you for considering supporting the Geo RGB community.
Before to start with QGIS, I would like to add a ID number to the Muse River dataset, because we are going to be working with the dataset. We are going to do some modifications, and I want to make sure that everything is good, okay? Then first, let's go to add here a column, and this column is going to be the ID number. Then we are going to add something from 1 to 155. That's the total number of samples that we have in this dataset. That's it. Then we can save and keep the same format. Now we can close, and now we can open the spreadsheet. Then let's go to select this option. Here, let's go to look for that file. It's in this folder, number 4, dataset, and it's this one over here. Open. Make sure we have selected this option over here. The geometry, we have to make sure X is with the X coordinate and Y is with the Y coordinates. And the projection that we are going to use today, I'm going to provide you now the code, is 28992. Is this one here. OK, and apply. The first option is good, and close. Now also we can add a satellite imagery from Google Satellite. Next thing is to add the perimeter of the area. I did already. Then we can add it. Make sure you have vector file selected here. And let's go to look for the file that is here, shapefile, and it's going to be this file over here, perimeter. Open, add, and close. Now we can make some additions over here to make the layer be transparent. Then it's going to be transparent. I want the color to be red, and also this one 0.3. Okay, apply and okay. Remember, if you want to create this layer, the things you have to do is just go to layer, create a new layer, new shapefile layer, add the information here related with that layer. For example, let's go to do, for this one, number 4 is this one, shapefile. I'm going to put here as a number ACE, save, then select the reference coordinate systems. In this case, it's going to be this one. Okay, and then you have to select what kind of geometry you want. In this case, it was a polygon. Then okay, and now press the button to edit that layer. Use this option over here, and now we are ready to create any new layer. For example, if we want to do the digitalization of this area, we are going to select all the nodes, and that's how you can create the layer I created. Then put an ID number. Okay, and that's it. I did the same, but for the perimeter of this area, just to make sure that I'm capturing all the data set. Now I'm going to remove this layer because I don't need it. Remove the layer. And I'm going to take also from this one, I'm going to remove that one here. From here to here, delete. Okay, and I did the same for the river, but the river, instead to have a polygon as a geometry, it is just a line. Okay, it's the same. Then you have to go here, create a layer, create a shapefile layer, and here for the geometry is going to be a line, okay, instead to be a polygon. And that's what I did. Now I'm going to load the river then. Press this option here. Make sure you have vector. Go here. River. Open. Add. And close. Now I'm going to make some additions here. Properties. I want the river to be blue color. Then I'm going to take this option and I want the line to be 0.4 with this option over here. Apply and OK. Now we have the data set, the perimeter, and the river. The next thing is calculate the matrix distance in order to know what is the minimum distance between two samples. In that way, we can get the resolution of our grid. Then here is going to be matrix distance, and we can select this algorithm. The input layer is going to be this one. The input unique ID field, this one is good. And then we are going to repeat, that's good. Then we can run. That one is going to generate a new layer where we can see the distance between the data points. And as you can see, the minimum distance between 2 points is 43.9. And the maximum distance is 4,440. But we are interested just in the minimum distance. Then as the minimum distance between two samples is around 40 meters, a pixel resolution of 40 by 40 is going to be good, right? Then we don't need to do something smaller because it doesn't worth it. It's going to be more costing, computational, because the grid is going to be smaller, but the resolution at the end is going to be the same. Then it's better just to work with something 40 by 40 or 50 by 50. By 40 by 40 is also good and is the same as we have in the Muse grid in R with the package SP. Now we can remove this layer because we are not going to use this information more. Okay, and now the next thing is to create the grid. Then we are going to go to Vector, Research Tool, Create Grid. Here, type of grid is going to be rectangle. Extension of the grid, we can put here the perimeter. Horizontal is going to be 40 and vertical is going to be 40. And for the rest of the parameters, that's good. Then we can run and close. Now we can cut this grid with the shape of our perimeter. Then go to Vector, Geoprocessing Tools, Clip. Here input layer is going to be grid and over layer is going to be the perimeter. Then we can run and close. And now we can remove this one over here. Now we can edit this layer. Let's go to make some transparency here. Transparency, apply, and OK. Then with this layer, you can make an idea how is going to be the pixels in your grid. We are not going to use this layer for anything, right? Just to give you a visual representation of the pixels inside of our perimeter. Remember that these pixels are going to have a dimension that is 40 by 40 meters. We can measure here 40 by 40, okay? Now the next step is to add inside of these rectangles the data set associated with the grid. To do that one, we are going to use the processing tools. If you don't have the processing tools, just go to processing toolbox. Then when we press here, processing toolbox is going to appear here. And now what we want to look is for regular points. Is this one over here, double click, and the extension, again, we are going to use the perimeter, and the point sparsing is going to be 40 meters, because we want a separation of 40 meters between the samples, and the initial inset from the corner is going to be 20 meters. Then we can run this one. Close, and again we can cut this one with the perimeter, right? Then go to Vector, Geoprocessing Tools, Clip. Now we want the regular points and the over layer is going to be the perimeter. Then we can run this one, close, and now we can remove this one over here, delete, okay. And now as you can see, let's go to take this one out at the moment. As you can see, inside of each rectangle, we have one point at the middle of the rectangle. That is going to be our data set related to the grid. The next thing that we want to do is to convert the river in a point. Because, let me take this one now. I'll put this one again, because what we want to calculate is the distance from each sample point to the river, but we cannot calculate the distance from point to a line. We can calculate the distance from point to a point, okay, with the next script. Then what we have to do is to convert the river in a point, okay. Then to do that one, we are going to use again the processing toolbox, and we are going to look for point along geometry. Is this one here, point along geometry. Double click to open. Let's go to select the river. Distance between the points is going to be 1, that's good, and then we can run this one. Close, and now if you make zoom, you are going to see that we have now points on the river, and that's what we want. Then for the next script, we are going to use the distance to the nearest hood. Copy, I'm going to show you here, is this script, paste, and we are going to use the line to hub. Double click to open. Source point layer is going to be the Muse data, our data set. For destination hubs layer, that one is going to be the interpolated points, is the line that we created for the river with points. The hub layer name attribute is going to be the ID. The measurement units is going to be meters. Then we can run this one and close. And now, as you can see with this script, what we get is the shortest distance between the sample and the river. But remember that the river now are points. It's no line, okay? At this point, we have to clarify one thing. If we have here the sample, and the brown line is the topography, and the blue line is the river, we are calculating the straight line, the straight distance from this point, that is the projection of the sample on this line, and this distance is the one we are calculating. That is different than the real distance. The real distance is going to be longer. This distance from here to here is known as a Euclidean distance, okay? And it's always shorter than the real distance, because the real distance has in consideration all the topography, right? That's something important that we have to consider in this case. For this exercise, the Euclidean distance is going to be good. Now, what we want is to export this data that we created to our data set, okay? If we open the attribute table of this new layer, you are going to see that we have all the parameters that we have in our data set, plus a new field that is that distance. The distance that we calculated from the sample to the river is this distance over here. And we want this distance to be added to our data set. In our data set, we have different distance to the river. It comes from the original data, is this parameter over here, distance, and this distance is the standardized distance from the sample location to the river. I'm not sure how they calculated this distance, but it's not something really important for this exercise. And also, I know this distance is the survey distance that they calculated when they was taking the samples. But also, I didn't know how they took it, that distance, right? But for me, it is not really important, because what we are going to use is the distance that we calculated in this exercise, okay? We are not going to use the original data. We are going to use our own data. Then to do that one, we have to export this file. Then to do that one, we are going to export here, save feature as, and here we are going to select this format, CSV, okay? Then here, make sure you have the coordinate reference systems. Is this one is good? It's not really important, but then here we are going to save this spreadsheet here at the data set with the name of distance to the river. Inside this folder, distance to river. And I'm going to add here Muse data. Okay, save, and the other things are good, then okay. And as you can see, now we have this new file added over here in the panel, okay? The next thing also is export this layer as a shapefile, because now if you check the attribute table, I mean the information, you are going to see that this file is the limited test, okay? And what we want here is a shapefile. Then we are going to export this one as a shapefile, then export as a feature, and then select here Esri shapefile. Then we are going to save this one here at the shapefiles as a Muse dataset. Save, and everything is good. Here is really important, the coordinates are good, and okay. And now we can remove this one, because we are not going to use this one more. Remove, okay, and I want this one with a different color. Then properties, symbology, and I want this one with a red color. Apply, and okay. Now we are going to add in this attribute table the distance that we calculated. Okay, we are going to add a new field here. Then to do that one, we are going to go to the attribute table. No, first we are going to go to properties, then select join. Here select this option to add a new join. Here I'm going to add this table, distance to river, the Muse data. Remember that is the distance that we extracted from here. Okay, this table has the same information as the attribute table in this layer. Then that's because I decided to add the ID number, because now we need that number in order to make sure that we can join the tables properly. Okay, and then for this one I'm going to select this one, and for the other one I'm going to select the same one. Okay, because you have to make sure that the ID number is a unique number. Okay, it means if you go to the attribute table here, I cannot open now. Let me this one take out. If you go here to the attribute table, this number has to be unique for each sample. Okay, and that's the reason, because we add from 1 to 51 to 55, and each number is different, right? And also here we can link this attribute table from here, from this layer, to the attribute table to this layer over here, and we can join both tables because of that ID number. Okay, then we can go here, properties, join, select the table, this one, that's good. Okay, apply, and okay. Now if you go to the attribute table, you are going to see that the fields has been added. Okay, now we have all these fields that has been added, but I don't want all this information. Okay, I'm going to edit a little bit this table. Then to do that one, in order to clean these values, right, because even I don't want so many decimals here, then I'm going to edit the attribute table, and I'm going to create a new field. This field is going to be distance to the river. Then here is going to be decimal number, and with 3 decimals is good. Then here, fields and values, I'm going to select the field I want. That is the last one, this one. This one over here is this one. Double click, and I'm going to multiply this one by 1. Okay. And now if you can see, now we have the new field added over here. Now I can close the attribute table, save. I can remove this layer over here because I don't need it more. Okay, and also I can remove this one here. Well, I'm going to leave this one at the moment. But now if you go to the Muse dataset, open attribute table, you're going to see that now we have this new field over here. That is the distance to the river that we calculated. Okay, and this one has some differences, but as I said before, don't worry about it. Okay, because we are going to use the data that we created. Then we can close this one here, and now we can do a scatter plot in order to see what is the relation between the zinc concentration and the distance to the river. Then let's go here, put here a scatter plot. It's going to be the first one. Then I want to use this vector layer. The X is going to be the distance to the river, and the Y is going to be the zinc concentration. Then we can run this one to see the scatter plot. Double click to open. But we also can use the script that we created at the second Geostatistics course in the first lesson. Is this script over here. It's going to be the same information, the Muse dataset. Here for X, what we want is the distance to the river. For Y, we want the zinc concentration. But here we can add the title, the subtitle, and the labels. I'm going to add the labels, but I'm going to pass the video faster. I already add all the information. Now I'm going to run the script. Double click to open. And I'm going to make this screen bigger. And as you can see in this graph, I added the title, scatter plot, zinc versus distance to the river. that is going to show the relation between the two variables. Here we have the zinc concentration in ppm, and here we have the distance to the river in meters. And as you can see in this graph, the relation between the two variables is not linear, right? Because we have a very strong curve over here, right? We cannot fit a linear model here. Then what we have to do is to modify these variables, make the transformation of these variables in order to see if we can have a linear relation between these two variables. And that's the next thing that we are going to do. Then go here, we can close this one. Go to the attribute table here, and now we are going to do some modifications. Then go to the raster calculator, open field calculator, sorry, and then here we are going to create a new field that is going to be log 10 of the zinc concentration. Then we are going to add here decimal number. This one is good. Then we are going to go to fields and values. Select the zinc concentration. Well, first what we have to do is to go to math. Here, select the log with base 10. Then add here the field related with the zinc concentration. That is this one, double click. Then we can close here. Okay. And now we created a new field related with the log 10 of the zinc concentration. And now we're going to do the same, but for the distance to the river. It's going to be log 10, distance, river, decimal number, math, log 10, field, is going to be this one. Okay. Now we can close this one, save, and we can do the same scatter plot, but now with the log 10. Then this one, no, this one, muse. Here is going to be the log 10 for distance to the river. Here is going to be the log 10 for the zinc concentration. And I'm going to add the labels, but I'm going to pass the video faster. I added already the variables. Now we can run this one. Double click to open. And now we can see that this scatter plot is showing a linear relation. Now we can fit here a linear, right, model. And as you can see, the relation is pretty clear. As we are closer to the river, when the distance is smaller, we have the highest concentrations for the zinc. And as we are going far from the river, the concentration of zinc is going to be less. And that's the relation between these two variables. Remember that, as I said at the introduction, when we are working with Kriging with external drift, we can only use linear models in our data. Then if we have something like that, and even after making the transformation, if we cannot make this relation to be linear, we cannot use Kriging with external drift. We can use only Kriging with external drift when the relation between the two variables can be fit in a linear model, okay? And that's the case. In other way, we have to use regression Kriging. Now, the next step is to work with the data associated with the grid. Then we are going to take this one out because now we are going to work with this data. The first thing that we need to do is to add coordinates to each of these points, because as you can see, if we go to the attribute table, open attribute table, we have just the ID, we don't have more information. Then let's go to add the coordinates, the X and Y, open attribute table, open the edition, open the field calculator, we are going to add the X coordinate. Then we want here decimal real number. Then here I'm going to put this one and this value over here. is to calculate the coordinates. We can press this option to see the help. As you can see, returns the x coordinate. Then double click to add over here. OK. And now we have the x coordinate. Now we are going to add the y coordinate. Then y. And I put here the same as before, but now with the y. Is this one. And returns the value for the y coordinate. Double click. OK. And now we have the x and y. And close edition. Save. In this case, it's really important to have a different ID for each point, okay? Because in this case, maybe a lot of sample locations or unsample locations, because these ones are going to be unsample locations, can have coordinates similar for y and x, okay? Then we have to make sure the ID numbers are different in order to do a proper grid with the distance to the river. That is the next thing that we are going to do now. Then paste here the script. We are going to use this one distance to the nearest hub, and we want to use the first one. Double click. In this case, we are going to add this one here, and the destination is going to be the interpolated points, that is the river. ID is good, and the measurements is going to be in meters. We are going to do the same as we did previously for the Muse data set, but now with the data associated with the grid. Then now we can run. And with the next layer, what we have is the minimum distance from each point from our grid to the river. Okay, then we can take this one out. Remember that, as I said at the introduction, for the variable that is going to act as external drift, we need to have that variable in our data set, but also in each unsampled location at the grid. And that's what we are doing now, add the distance to the river in the grid. Now what we want is to export the information in this attribute table that has the distance from each unsampled location to the river for all the points that in total we have in this grid 3,153 to the data set. The data set is this one. Then first let's go to export this table. Export, save feature as. Here we want this format, CSV. Let's go to save here at the data set. Distance to the river. Here I'm going to add grid. Then save. The rest of the parameters is okay. Okay. Now we have the table here. Now we go to clip. In clip, go to properties. Go to joins. Add the table here. Is this table. We want to join by the attribute ID in both cases. And OK. Apply. And OK. Now if we go to the attribute table here, you can see that the fields has been added. Now what we want is to clean this value a little bit. Then let's go to press this button to edit the attribute table. Here we are going to add the parameter distance to the river. Sorry, distance river. Then here I'm going to put decimal. This one is okay. I'm going to go to fields and values. Select the last one, that is the distance to the river. This one here, double click, and I'm going to multiply this one by 1. Okay. And that's it. Now we have the new field added over here. Now we can close the edition, save. We can close these windows here. And now we can remove this table over here. Remove the table. Okay, and if you go here now to the clip and open the attribute table, we have the distance to the river for each unsampled location. Now I'm going to save the project just in case. For this one, I'm going to put Kriging with external drift. Save. Oh, I have to put a different name. Kriging external drift QGIS. Save. Okay, and now as this layer, the Muse grid, is a temporal file, as you can see over here, we're going to export just to save this file. Okay, then export, save feature as. Here we have to select save file. Let's go to select a name for this one. That is going to be the same as this one, but Muse grid. Save. Geometry is going to be point. And okay. Okay, here we have a problem that is saying that we want to save a layer that is multi-point as a point, and it is not allowed, right? Then what we have to do is convert this layer to a point. Then to do that one, we are going to use the next script. Paste is going to be this one. This one allows us to convert the vector layer just a simple point. Then I want to convert this layer, is the one I put it over here. And also I'm going to save right away, right? Save file. And I'm going to save here for save files. And this one has to be save files. And I'm going to remove this one. And I'm going to save with this name. Yes. And run. Close. And now I already saved the layer, Muse grid. Then I can open. And as you can see, we have the X, Y, and the distance to the river. Then we no longer need this one. Remove this one. Okay. And that's what we need, right? We need the grid and we need the data set. And the data set has the distance to the river, and the grid has the same parameter, distance to the river. In this case, in this grid, we add the distance to the river, right? But we can add any other variable. For example, the type of soil, the geology, any other parameter, right? What you have to do is just add the vector layer related with the parameter that you want to add, for example, type of soil, then select all the points that are inside that polygon and assign a number for that points, okay? That's pretty easy. Then in that way you can add any other variable in this grid. That's what we can see over here, right? In this kind of map. Here we have the type of soil, and and here we have the flow frequency. And if you have the cartography for the type of soil or the cartography for the flow frequency, you can add those vector layers here on the top and then select the points to that vector layers and then assign a different value for each of the features, right? Then you are going to have a map like this one, right? With the type of soil and also with the flow frequency. But we are not going to do that one here because I believe the distance to the river, it was a complex thing, but for the other ones it's pretty simple, right? It's very straightforward. The last thing that we are going to do today is to convert this vector layer to a raster file. To do that one, we are going to use a different script. Let me copy this one. It's just a rasterize. Then is this option over here, rasterize vector to raster. Then double click. And here we are going to use the Muse grid, is this one. Then here the parameter that we want to use, in this case is going to be distance to the river. We are not going to add anything here. Here we are going to use the georeference units. Here we are going to add the pixel dimension that is going to be 40 by 40. And that's it. We can save this file also. In this folder, here I'm going to create a new folder that is going to be raster. And I'm going to save inside this folder as raster, like this, save. And then we can run. Close, and now we can edit this one a little bit. Properties. We can go here, single pseudo color, equal intervals, and we are going to add 8, for example. Apply, and also we can put this one as a discrete. Apply, and OK. And that is the same as we have over here with R. This one over here. But here we have 1, 2, 3, 4, 5 classes, and we put it 8 classes. But you can put the number of classes you want, right? 5 classes, and also with a different ramp of colors. This one, for example, apply, or the blue one, apply, is the same, okay? This one as this one over here. Also, we can put on the top the grid that we created at the beginning of this lesson here with the pixel to see how it matched perfectly, right? The 40 by 40 that we created at the beginning. Then also, if you add the points associated with the muse grid, you can see that each point is at the middle of a square, right? Everything is matching now. Also, you can put on the top the Muse River data set to see where is located your samples. And also we can add the distance to the river, not for this one, for the other one, that it was this one. And then you can present the map as you want, right? You have a lot of different options here with QGIS, right? The edition, it's more easy to do with QGIS than with RStudio. Also, in this case, we didn't interpolate anything, right? Because the value that we have here, for example, for each pixel is the same value that we have here at the point of the grid. We didn't interpolate anything. Now, the only thing we did with this raster is just to assign for all this area the value that we have in this point. Okay, let me show you. If we go here, information, and we select this point over here, the value that we have for the distance is 63.281, right? And if we select this pixel, then we can go here and then select this pixel, you are going to see that we have the same value, okay? We didn't interpolate anything. The only thing we did is just assign to all this area the value that we have at the vector point, okay? And that happens for all the points and for all the pixels, okay? That's how it works, this raster. It's not an interpolation, okay? It's just putting the value of the vector point on the pixel, okay? That's it for today. For the next lesson, we are going to do the interpolation for Kriging with external drift. And with R, we are going to export all the things that we did with QGIS to RStudio, and then we are going to do the geostatistical analysis on RStudio. But that is going to be part of the next lesson. Thank you very much for watching this tutorial, and see you on the next one.